the topic of today. So this is following up from the stuff we did in lab. This is really, the lab was just a pretty basic introduction to kind of ideas of randomness. And I've told you guys over and over again that computation is first and foremost about numbers, right? It's like you take a number as some kind of input and it outputs a form or something that eventually leads to a form. We've seen the sliders, right, as a way of inputting a number that we can change like manually. We've done things like series and range, so we get like a collection of numbers that has a particular order to them, right? We make a lot of numbers and we get a lot of things. We've done the graph mapper, which is a way of graphically creating numbers, right, that are following along a mathematical curve. And then lastly, we have randomness now. So now we can essentially make a collection of numbers that are random that have some kind of attribute. So we've said they have what? They're within a certain range, right? They can only be between 1 and 100 or between 50 and 75 or whatever, right? So there's a range that we want to get. And we can define that parametrically using a construct domain. We can say how many numbers we want. The last piece of this is the seed. And I get asked a couple questions about what a seed is. So let me actually take a look at this in the system so you guys have a sense of what I'm talking about here. All right, so let's drop a panel. And domain. We're going to construct the domain. So the range here, a little bit different than the way the component looked in the files I gave you because it was the old Grasshopper. The only thing that's different was it had that I for integer. If you right-click this, you can check the box for integer numbers. That's where that I went. It went inside the component. Okay. Otherwise, it's exactly the same. I'm not giving anything different. So we want a range, and we have an A and B, which we can use with a number slider. So I'm going to go ahead and drop let's do 0 to 100 for both of these as natural numbers. Okay. So A and B. Oops, close enough. Okay. And then we have an N for number and an S for seed. Of course, N can't be 0 because we get nothing. And our ranges can't be the same because then we don't get anything random. Let me make this bigger for you guys. Okay. Okay, so that's what we get. I ask for 10 numbers, I get 10 numbers. The range is between 0 and 21. Okay, so we talked about the seed. And let's look at 0 right now. It's 15.25 and a bunch of garbage. Okay, right? And I asked you guys a question, if you change the seed to something else, so I change it to some other number, and I get a different number for 0. But if I change it back to 0, it's the same number. Okay? And that's really key. I asked you guys this question about, is it really random? Okay, and what's the answer to that? No? Okay. Did we know that it was going to be 15 when we started the component? No. But now we do, right? So the answer is kind of yes and no. I mean, no, because if it were truly random, we can never get back the same number. And to that, I definitely agree with you guys. But the fact is that these are pretty much numbers that we wouldn't have any foresight about. We wouldn't know that these numbers would actually come out of this system. So there's some algorithm in Grasshopper that generates random numbers in what we call a pseudo-random way. It's functionally, random, but it's also something that we can, if we make this component exactly the way it is and we give it to somebody else, you'll get the same number. Okay, so. It's random and it's not random. Okay, but the idea is that, and I've said this, it's like parametric randomness. Okay, so if I change the number of things, it's not like it re-rolls the random numbers. It just removes some of those numbers from the list. Okay, and if I change the seed again, I can always go back to that number. Okay, so it's almost like pre-computed in a way. It's not though. It's actually computed, but it's computed in a way that's consistent. So it is, for all intents and purposes, it's random, but it has these parametric properties because that's what we want in terms of a design process. What's great about this is that if you find something that you like in the random numbers, you can get it back. Okay? I think I've said this to some of you guys in lab. When I'm like writing random number generators for some of the software that I'm writing, it's truly random. Like if I see something, I'd better capture it in some way or find out what that was, because I'll never get it back, because it's random every single time the program runs. Okay. Just for a little aside about how random number generators like work, in case you're interested, we typically in some of the algorithm, there's some thing that's used as, there's always a seed anyway. But in the algorithms that you're seeing in software, like in like video games and things that need to generate random numbers, what it's doing is usually taking the time. So it's like in microseconds from the time you boot up your Xbox or from like the internet or something like that. It's looking for specific, because time's always like changing, right? And if you catch a time that's very fast, like again down to the microsecond or whatever, chances are, I mean, even if I tried to do it like every second, it's going to catch a different set of decimals at the end of that, and that's what it uses as its random seed. And so it feeds it into some algorithm. You like divide a number, add a number, and then that's your random number. Okay? But because time's always moving and the slice of time is always changing, that's where the randomness comes from. All right? There's other ways of doing it too. There was a website that was really famous because it was a random number generator that used a lava lamp, basically, right? And what it did was it had a camera that was pointed at the lava lamp, and as the lava would like ooze and like whatever, there was a machine vision algorithm that would look at that shape and calculate the area of it, let's say, and that would be the random number. And that thing you could never predict. Like you could never figure out what that was. Catching time, if you know the algorithm that does it and you know how fast it's catching and you know when it started, you can actually you can predict the random number. It's very, very hard to do, but it's unsecure. The lava lamp was actually great because it was very secure. Like there's no way to know like what that would actually produce. Okay, that's a little esoteric. But anyway, random numbers are a really popular thing because we use them to generate passwords that the banks use, like when you're transferring like money, because it's ultra secure. You use them because, you know, in like a video game, you know, you don't want the same thing to always like happen. You want all the enemies to spawn in different like areas with like different loadouts or whatever. It keeps things interesting. Okay, and we'll talk a little bit more about that. But random numbers are everywhere in like computation. Okay, whether we've talked, a lot of the data we've done right now is very like strict. Like we know what it is, we know what the quantity is. Okay, but random numbers are used like a lot of things, like when we want to simulate something, right? Because we can't completely simulate something, so we add a little bit of like friction to it, a little bit of like dirtiness to it. That's where random numbers come in. Okay, and that's why we're interested in them as designers. So we'll talk about that a lot today. Okay, any questions about any of that? Does that all interest you? All right, randomness. So there's lots of different ways to generate randomness, as I've said, and we see you know, things like games of chance, talk about like roulette, you know, drawing cards, rolling dice, throwing darts at dartboards, right? All kinds of ways to introduce randomness. Towards what end? Let's look at some projects that have like some kind of randomness in them. And I do this often. I just go through Arch Daily and I like pull projects, and I'm like, this is an example of this. I don't know if the architects actually did this, but look at the facade of the building, right? It's this essentially, let's say the whole thing started off red, and there was kind of maybe a random reduce or something where they started to like throw out those, they started to change them, make them white. So it kind of like dissolves, but it doesn't dissolve in a regular way, right? It's not a gradient. It's kind of, it's just kind of like eroded. You know, sometimes the erosion goes all the way, you know, down to here. Sometimes it's almost kind of solid, like all the way up, but it just kind of erodes. And like that just may be what the architects intended. And it's more interesting than, let's say, a checker, you know, pattern that's really regular, or the whole thing being red, or the whole thing being striped like a circus tent. It's kind of like interesting, kind of techy, right? And you could certainly write an algorithm that would do something like this, and it would be parametric. Okay, let's take a look at it. So what this is a lot like the that sort of like garage precedent, where there are these kind of panels that are kind of like woven in and out of something, but some of them are red and some of them are white. And there's once they designed it, they had a plan, and they just knew where to install the red and the white panels. Okay. Sometimes they don't do things like this. Sometimes, like when you do like a brick wall, you'll specify the kind of brick, but the bricks will be fired differently. They'll come from different like parts of clay. They're handled differently, and so like you have a bunch of bricks, and the mason makes the wall. The mason just puts the bricks up and doesn't look at them, and the wall is kind of like random, right? There might have been an instruction for this that just says, here's a bunch of these panels and we're just going to install them as we go, and eventually you start to run out of like red ones, and maybe that's how this thing got the way it is. There's lots of different ways to introduce this into the process, okay? I think it was planned. I think it was pretty strategically planned. Let's take a look at that algorithm, okay? So I've got these scripts, and like I say all the time, I'll put these online for you guys. Let me just find them here. One second. Everybody look at my directories. Okay. Okay. And there's actually like a ton of them in this one. Whatever. Okay. You might not like me. Okay. So the first one is erosion, I'm going to call this one, right? And it's not the same as random reduce. Remember what random reduce does, basically, right? It just sort of starts to throw things out like willy-nilly, right? Why is this not the same as random reduce?
Controls which direction they're...
Yeah, it's like eroding from the like top, right? It's reducing more from some area than it is from another area. Very good. That's exactly right. We can control this. And that's a theme that's going to be running through today, is the idea that even though it's randomness, we are in control of it. Like, we choose the kind of randomness that it is, we choose the parameters of the randomness, and we choose the output that we want, okay? You're the designer. The computer doesn't like design this stuff. Like, when you get something that comes out of this, you choose whether you want to build it or not, and you choose whether you want to edit it or not. Like, I might come up with this thing, and this facade's like okay, but there's a little bit too many tiles at the top. I can change those. Like, I don't have to like stick with what the computer gives me. Okay. And it might sound really, just sort of like, that might sound obvious, but I think sometimes it's not obvious to people. Okay. You can mess with this stuff after it comes out of the computer. And in fact, a lot of the stuff that you're seeing has been messed with, basically. Architects, when they're presenting their lectures to us, when you see their great work online, they kind of tell you that they wrote a program to do it. But the program was like part of the process. The architects were still fidgeting with it, trying to make it look as good as good as they could, or making it less rough than it was. Okay, the architect is intimately involved in that process. Okay, it's not hands off because the computer was involved. The computer is like, I'm saying this. The computer is like an intern. I think I told you guys this in the studio or in the lab, right? The computer's just giving you options, right? It's your slave, and then you decide like what you want to do with it. Okay. Okay, so let's take a look at erosion. And I believe this is a front view. If I'm wrong, I don't have to do a top view. So all these reference a surface. Yeah, and I need to turn it on too. Okay. And I'll go back and talk about. Oh, as a matter of fact, it might be. Nope, it is. Yeah, it's a Z. Okay. Okay, so turn these both on here. Okay, I need to adjust this a bit. Yes. Okay, and actually this one is not going to work as well. So the way that this one works is as follows. So I have a surface, I divide it up, I explode it, and in order to erode it, what I do is I look at the Z coordinate, right? Because that's actually like what's up above, right? And I want to remove things that have a higher Z coordinate. So I take the center of each of these tiles and I extract, I decompose it to get the Z of that, right? And then when I set my random numbers up, I can control through the sliders where I pick my random numbers from, and I want to pick my random numbers more up here, like more in the Z than like down here, right? And that filtering is actually what's going to give me that erosion. Now, this has to be, tuned a bit. So this is what I've got right now. It's not working so hot. So I need to go through and I need to adjust. I need to adjust this a bit more. And it's actually, I think the way I've set this up is actually going to be troublesome here. Let's see. And I have a bounds component. Yeah, which shows me, so it's between, the z coordinates are between like 0, let's say, and 24. So I probably want these to be between 24 and then some other, and I need to have my mouse on this to actually see where this is happening. And, you know, I can change the, yeah, it's changing. You have to play with this on your own, maybe, but I can change the seed. You know, to get it, I can change the threshold, and it's not basically what I'm doing is I'm taking these random numbers and I'm testing them to see whether they are above the line that I want to start removing them from, and that's what's going to give me that kind of erosion. I'll show you. I have another example of this that I'll show later, but that's the idea. So the idea is that you have randomness, but you're testing it in a specific way, and that's going to get me to remove more of the things that I want. So again, I'm looking for random numbers that are mostly in that upper kind of z range, and that's what's going to be more likely to remove them than a random reduce. Okay.
Is that what's not working well?
Yeah, right now it's I think the thresholds are not set up too well. I have another example that I'm going to show you that works a lot better.
So it's uniform.
It's right now the range is, yeah, exactly. It's essentially a random reduce. I mean, to be honest, it's not. I think I made the surface too small. Is actually what's happening. So it's not working the way I want it to, basically. But I might even have to fix this one. But yeah, the other example does a little bit better job of it. But it's the same principle as is in the other example. But yeah, it doesn't work that well. Anyway, I'll show you. It's actually going to be coming up in a second here. The other piece I want to talk about, the other kind of randomness that we have access to, is this thing that's called pick and choose. And this is really useful when you have like a modular design system. We talked about at least in second year, I know with you guys, and I think the graduate students have talked about this. Modularity is one of our design themes that we have. And it's this idea that you have maybe a kit of parts, and they have a specific module, like maybe there's like an A, B, and a C, and then you have different rhythms that you set up. And we talked about there being rhythm, but there's also an idea that there's like a discordancy where maybe I just randomly, it's like A, C, B, B, A, C, B, A, B, whatever, like gobbledygook. But because they're all like modular, there's an order like to it in a certain way. Because you've actually designed what the modules are, but you maybe don't care about exactly how they're arranged. Okay, and that's kind of what's going on in this design here. There are these different like sizes of windows and different sizes of panels and different kinds of glass. There's translucent glass and transparent glass, and they're just all in a big like box of Legos that somebody shook up, and then they just put them back in order, you know, in this building, and that's what creates the pattern on the facade. If you look for this kind of stuff, it shows up like all over the place. It's a very contemporary kind of idea. It gives this very complex appearance of the facade, right? I don't think some intern like sat down and designed like how this thing was really laid out. There's just probably a system for like designing this, right? And you can do that. And there's actually, you know, and this is what it looks like. This is what the facade. So the back is a very like normal facade. I mean, I'm sorry, the south is a normal facade. The west has this very interesting kind of patterned facade. So we'll take a look at pick and choose here. And I may need to make these things bigger if they're not going to work with my script. Okay, so I'll turn this on, T and C. Oh, and this one is the wrong direction. Okay, so this is one that works on the top. Yeah, okay, so we'll reference a surface from the top here. I might make a note of that in the script. Ah, here we go. Okay. So this is what it looks like, and so just assume there's like the other one. There's three things. There's the circles and the rectangles and the squares, basically. I'm sorry, squares, triangles, and circles, and they're A, B, C. And what this algorithm does, so we just divide the surface up. We get a bunch of points. We generate a random number between 0 and 2. So 0, 1, or 2, right? And this is actually one where I've said I want it to be integers only, and so I get a list of instructions from the computer that says 0, 1, 1, 2, and that's our ABC. Okay? And then I've got my three shapes. And then what I have to do though, this is where I don't like this component very well. There's probably ways to do this better, but basically I make 3 batches of these things where I fill the entire thing with circles, with rectangles, like with whatever. That's what these 3 are. And then pick and choose, or P and C, right, takes these 3 inputs, 0, 1, 2, and then it uses this pattern to like basically redistribute them. Okay? And that's what pick and choose is doing. So it takes that list of 0, 1, 2, and it just pulls those things out. Now this could be any geometry that you can reference, right? You can make the windows, you can have different colors of things, right? That's your system, okay? And that's the way that you can distribute them. There's other things you can do with this besides this, but so pick and choose is one way to randomly pick things that you have. And P and C, like you can add as many things as you want in this list. You can just keep adding numbers to it. So it starts off by default with like 2, 0, 1. And you just keep adding. If you zoom in, you can keep adding numbers to it. Okay? And you just plug stuff into it. That only shows up when you zoom in. It's kind of weird. You can remove them too. So pick and choose is another way. So it's just a...
What's plugged into pattern?
Yeah, it's the random numbers. Let me throw a panel. Let me throw a panel out there. So I made a bunch of random numbers between 0 and 2, and that's it. So it's just 1, 1, 2, 2, 0, 2, 1, 0, etc. And that's the pattern that it is. Yeah. So that's the plan, and then the thing carries out the plan, basically. Again, you can use this for a lot of different things, but in this case, I'm using just shapes, because it's a simple thing. Okay. Yeah. Okay. Let me make sure that this is, yeah, okay. Let's go ahead and talk about another one here. So I'll go ahead and hide this one. And I'll go ahead and turn on this next one, because it's kind of related to it. Oh, darn it. Is this going to be, oh yeah, okay. Similarly to the last one, is this one that I'm calling random dispatch. And so you guys remember that the dispatch component was something that we saw a lot of use in like the logic piece that I showed like 2 weeks ago, right? And dispatch does what? We have a list of stuff that we plug into it, and then we have a true-false mask, right? And true goes to A and false goes to B. We like dispatch 2 things to different like quantities, okay? So they're using the same principle as we use for pick and choose, right? If we just do random numbers between 1 and 0, that's our true-false, right? Because 1 and 0 are true and false, right? That's basically binary. So what I have is a random number, and it's just between 1 and 0. And I have a seed, and basically, just like we were just talking about, the pattern that it produces are 1s and 0s. The 1s and 0s go into dispatch, and that gives us whether it's a circle or a rectangle. So it's just like, we don't care, just give us circles or rectangles, okay? And again, you don't like that, pattern? Try another seed, right? And these are they're kind of similar, but just an idea. Okay, so just if you want to create that kind of randomness between 2 options, a dispatch is just a quick way to do that. Okay, so you can filter by some test, like we did before unsuccessfully with the z-coordinate. Like we're looking at the z-coordinate as a factor in whether something is like a true or false. In that case, we did a larger than or greater than. And in this case, we're just looking for basically a random number to be our true-false. Okay? So you're always, like, when you do randomness, you can just throw things out randomly, but it's always good to have a filter on that randomness, right? To say, like, I want these things and not those things. Or I want more of this and less of that, right? Like, I want to remove more tiles from the top and less from the, like, bottom. Okay? If it's just random, it's like garbage, right? We'll talk about that in a second. This is still kind of garbagey, but you choose what the shapes are. You choose whether the output is like the way you want it to be. Okay, and that's where the design part comes in. Let's look at another example of randomness here. This is I believe it's a Dutch project. In this case, the randomness is like basically color. That's another factor, like in sort of in the way that we saw in the in the first example, where it's basically just a pattern of color. Here, it's actually much more like complex, right? The kind of optical effect that this is this is making, okay? And the point I want to illustrate, so this could be like a pick and choose to a certain degree. The key though is which colors are you putting into the like scheme, right? In order to make this optical effect, like the colors are themselves, like the choice of the palette is not random. Like that's where the architect comes in, is to decide what colors are going to set up like a discordance or are gonna create a visual field in the way that I want. And so you can see like this side. You can see that actually there are these almost stripes. There's like a red and a blue, but then intermingled between that, there's some green and some yellow or whatever. I'm not sure if you guys can see that as well as I can on my screen. And then certainly up on top, there's a lighter palette. There are actually these white bars in between them. So again, it's not like this idea of whether something is like purely random or not is something you really have to think about. Because this could, if it was just a bunch of colored crayons or whatever, and we just lay them out, it could easily become like terrible. So there's still some order in this that the architect is selecting. And in fact, this is actually what it looks like. There are these sort of like coded materials. And actually, what they did was behind these are the stripes, and then in front of it are like tones of those colors. In between those like colors, okay. If you ever want to talk about randomly choosing colors, like generating colors computationally, I could do like a whole thesis on it. Like it's actually incredibly hard to do because if you know there's all different types of information that goes into a color. There's like you could do red, green, blue, cyan, yellow, magenta, right? Those are all numbers, okay? You could do hue, saturation, balance, anything in Photoshop, right? But the algorithm to choose colors that are complementary and then to choose them like randomly can get really complex. You guys know the Adobe thing called Cooler, I think it's called Color, K-U-L-U-R? You know what? Yeah, that has a really good like matching algorithm. Basically, you give it 2 or 3 colors and it gives you all of the complementary colors for it. So it's possible to do, but to do so with this kind of complexity is actually an interesting computational problem. So check out Color or Cooler. So this is the palette that the architects chose, and this is a drawing of how these things are arranged. And again, I don't think they actually sat down and actually drew what all these are. I think this is computationally like generated, but it's drawing from this palette, and it's drawing with a particular set of proportions of these. So I think they're evenly distributed throughout. And they're distributed in a way that's like complementary. There's a dark band and a light band, so there's a lot of design in this that goes into it. And then the randomness is just a way of accomplishing that design objective. Okay. Pretty striking though, right? Like pretty crazy. And of course, there's windows behind those bars. But I defy you. It actually seems like there might be, some kind of order in here, but it's shifted slightly. We'll talk about that in a little bit too. So you can start with a rhythm and then you can jitter it. So you can say like, okay, so everything's like on a grid, but then sometimes they move like one way and move a little, ways. And that's another way to introduce a little bit of randomness into this. Otherwise, it's just going to be just a grid. But you can see like they're not lining up like these greens. Try to find the pattern in that. I don't think there is. I think there's some order, but I think there's also some randomness in that as well. Pretty cool. Okay. This is at NYU. This is in, I want to say it's a library. Does anybody know this project? Okay, this is a little morbid, but this is a curtain. It's a wooden curtain that's on these slats, and its function is to prevent people from throwing themselves off of the railings or whatever. They had a problem with suicides there. So it's aesthetic, but it's also like a safety feature. So it allows for people to like see through, but it's certainly not something that like objects can pass through. I don't know where to go with that, but the idea of it, the reason why it's in my slideshow is because this is actually kind of a mason's project. So in the way that I said that the masons had like these bricks and they just kind of assemble walls of them, there are these were assembled, and there are different size pieces that are kind of put onto these cables or whatever, and then there are spacers, and they're just randomly assembled basically. So there's an order to this, but it's just in when the way it gets assembled is what produces the randomness. You just pick up a spacer, put in a block, pick up a spacer, put in a block, and they just hang these things together, and that's what creates this. But somebody had to think of like what the proportions of these are, what the spacers are, what the blocks are, and then install that. And it's actually, the proportions of it are based upon the proportions of the wood railings. The material of it is selected so that it blends in with the wood. So it's a very like, and there are actually bits of it that are left open at the floors so that you understand. So it's not like monolithic. It actually sort of responds to the human scale when it intersects with a railing. So there's lots of design choices in this. But again, randomness is something that was added to the design to create visual interest. Okay. Yamaha. I can't remember what exactly. This is like a corporate building for Yamaha, and Yamaha pianos, as a matter of fact. So there's Yamaha motorcycles and things like that. And it's got this nice kind of night reversal where it lights up. But what it is it's a facade system that has these different kind of panels of glass. Some of them are opaque, some of them are transparent, colored, not colored. It even goes to the inside of the space where that paneling is actually used in the acoustics of the space. So there's different like kinds of panels that are arranged in this diagonal checker system. So the logic of it like actually goes throughout the building. I'm going to show you like, hopefully my script works here, like how you could do something like that in your project. Worked. Fantastic. So let's take a step back. So that's the result. Like I basically duplicated it for all intents and purposes. Not too bad, right? Pretty close. Okay. So let's take a look at this. Let's go all the way back. We'll turn off all this junk here. So the first thing that I did was create basically the setup for it. So I needed, my surface. In this case, I used a tri-grid because it automatically gives me these like diagonal things. You could basically come up with any set of objects that you want to start to apply these like colors to, or that you want to select something from. Now, if you're going to use color in Grasshopper, and I may be wrong about this in the new version, but basically surfaces don't have color, but meshes do. Okay, let me be clear about that. Meshes have color. If you want to do anything with it. Now, what's a surface? What's a mesh? Surfaces are the things. They're basically like mathematical approximations. They're NURBS. Okay, so they're the kinds of things that are kind of swoopy and that are kind of flowy. Okay, meshes are more like polygons. They're like video game characters. They're like Tron, right? They're kind of boxy. They're kind of faceted. Okay, surfaces, are meshes, but they're just really, really fine meshes, right? Meshes just are meshes. Like they are like simpler geometric representations. Okay. What you can do though is, and the reason why meshes are important is because everything in the computer that you see in 3D is actually a mesh. That's how the computer understands like how to like render it. The surface is just another kind of math that we work with, and we mostly work with surfaces in Rhino. We use meshes when we use programs like Studio Max, when we're modeling stuff for animation or for video games, but Rhino can do both. Anyway, meshes are important because they can actually contain color data like within the mesh itself. Surfaces need a material applied to them. Okay. Okay, so what I have to do is I have to turn my surfaces into a mesh so that I can get the color, basically. That's what I'm telling you. So to do that, there's a really simple like tool. If you have a surface that you made, you can create what's called a boundary surface. And what that's going to do is essentially, so that takes my curves and converts them into surfaces. Then I can break those down into the faces, and then the faces can be turned into meshes with a simple mesh. So again, I'm taking the curves and I'm making surfaces out of them, each of those individual ones, and then I'm taking the faces of them and making them into meshes. And so things like this, like surface mesh or like mesh approximation, will essentially make these all meshes. So now I've got this green thing.
What are the other parts of the surfaces that are not the face? Like what's the eye and the V?
Edges and vertices. Yeah, this is just a explode like B-rep thing. Yeah, we've used that before. Again, a mesh. The meshes are either 3 points or 4 points, right? So like if you have 3 points, you have a triangle. That's a mesh, right? Just a dumb like triangle. 4 points is a mesh that's 2 triangles. You go back to geometry, okay? But meshes are just very simple objects. I threw on this mesh edges component because I want to see the edges of it. If you don't have that, you actually, well, it's actually turned on elsewhere, but it's helpful just to see the edges. So if you look at my script, I don't talk about meshes much except for this. That's what's going on here. Okay, so what I do is, then I have a component called mesh color. And so I can take a mesh and I can take a list of color data and I can apply it to each like mesh, okay? And that's where this is all starting to like work. There's actually a lot of new stuff here. This component is called an image sampler, and this is pretty neat. We can talk about this more later if you guys are interested, but images are data, right? We talk about like data structures. An image is a data structure, right? It's a set of x, y coordinates and a color, right? 3 kinds of data that are all correlated together, right? At this position in this image, this pixel is this color. I get enough of that data together, I get an image, right? So I can get x data, y data, and color data, which is actually 3 more numbers, right? Usually an R, G, and a B from that. So there's maybe 5 pieces of data for every single pixel in an image. And what the image sampler does is it allows me to take a set of coordinates, like x, y coordinates, and an image, and return the data that's at those coordinates. Okay, does that make sense? Okay.
What does it do where, like, so this has an arbitrary number of centers.
Yeah.
That doesn't have infinite pixels, so like where they don't.
That's why it's a sampler. So what we're doing
It's
is
like starting it at the bottom of the list.
what happens is a great question. So the samples I'm taking are the centers of each of these triangles. Like that's what I'm using. I'm using the area component to get those center points. Okay. Then I go into the image. So I made this image in Illustrator. Just full disclosure, I just made this thing. I actually picked the colors with the eyedropper from the image, and I drew these like stripes in Illustrator. I saved this file. I referenced it. So what I do is I set the x domain and the y domain to be the x distance here and the y distance here, and that's going to help these like correspond to a location on the image.
Okay.
Yeah.
So it doesn't matter really how many pixels are in the original image because you said like how
It could be a huge image.
Whatever it actually is, I've got 77.
Yeah. I think the resolution matters, right? Because if it was a crummy image and you didn't have enough things, I think you get weird colors, you get gray things. You need enough so that the samples are like meaningful. And that's a really, really good question. So do you guys understand what she's saying? Like she's asking like, basically like how do you know that you're able to get this information out of the image? Again, I'm cheating, like basically. I took this image. The proportions are really close to what I'm making. In fact, you could take this image in Photoshop or Illustrator, use it as an underlay, and then make your image based on these proportions. That would be a really smart move, right? I can draw this. Then I set the x domain and the y domain to be the dimensions of this, which I can get. Let me show you. So what I did was I basically took the size of the cell times the number of units, right? And that'll give me the length of it. And I took the height of it, the number of cells and the height times the cell size, and that gave me the height of it, right? Really simple. Like so I took 2 multiplication things, 77, 87, and change. 77, 87. That's how I did it. I wish you could do it parametrically, because then I could change it. It's kind of dumb. Anyway, so then what you can do is you can actually say I want to extract this channel from the image. I want the saturation, I want the hue, all the data I talked about, right? Because every color can actually give us that data in that image, right? It's actually brilliant. And you can tile it, so if you don't have enough data, it'll actually repeat this image until it fills up the range you've given it. So that's another thing. If your image is too small, you can tile it. This one I just cheated. It's not actually, it's tiled but doesn't need to tile because it's big enough. So what I'm extracting is just the colors from it. I want the color data. Okay, I'll show you examples. I can take an image, guys. I can take a black and white image. Remember I talked about bump maps before, displacement maps that make things push in and out. I can take an image that's black and white of a president's face or whatever, right? The black and white values of the image, and I can use those as data to push my facade in and out or something like that, right? Any data I can extract from an image gives me numbers. Numbers let me adjust things parametrically. So this is really valuable if you want to work with images as a data source, okay? I'm using it just for color. It's kind of dumb, but what are you going to do? So immediately what this gives me is that. And you'll notice, and this is actually getting to your point, where it gets very close to the edge of something like that, it kind of missampled a color. Okay, I can tweak that range if I'm really die hard about not getting it. I kind of like the irregularity. I'm going to keep that. Okay, but that's what happens. That's kind of a weird one too. Depending upon your image compression too, if you do a really messy JPEG, you can get really weird artifacts in your stuff too. Okay, so mesh color. And this is very important. The data structure is important because I want to take a color from a position to a particular mesh, and so the two have to be grafted together. And the way that our lofts have to be like grafted, I got to graph these together. Okay, so I got that. And then what I did was, and this is Josh, I think where it's going to work. The same idea that I had with the because what's happening in the facade, I think, is that there's this pattern, but then it's being eroded. So the white ones are the parts that are eroded, but the original pattern are these like tiger stripes, these Yamaha wooden stripes. Okay, and so that was my thesis, my hypothesis. So this is the height, So the base of it is 0. The height of it we've established is like 77 or whatever. We said that's the height. I deconstruct the points, so I know that's where those points are in that range. Same thing as last time. Oh, except this time I used a smaller. I think that was my problem. I used a larger than component. I wanted a smaller than component. These are the random numbers that are produced. Dispatch goes to 2 meshes. This is what's left from the dissolved piece. And the other piece I add. You can make a color component. So if I actually drop a color. These little black checker things, right? I can right click it and I can actually set the color. You have a little color picker. So that becomes a little paint chip. Plug that color in for the mesh. So now I've got this mesh and now it's white. And if I turn this on, I get the facade. Okay. And just to prove my point, let me turn all this stuff off here. This is my thing. It's totally random. And depending upon how I do that, right? I can dissolve that more or less. Okay. So this is better than the other one.
What's the LNG component?
That's the length of the list. I'm choosing a random. I want a random number for every single one of these tiles to decide its fate, basically. But some of them I'm putting my thumb on the scale because they'll never get picked because they don't fall within that range. That makes sense? It's a lot to talk about, and just between us, take a look at the script if it interests you, and ask if you guys have questions about it, let me know. But this is a pretty good demonstration of that principle from the earlier one, and about how to use color. Now, Nick, you might be saying, well, you will say, if you try to render this, nothing will happen. It won't output the color because it's color data that's attributed to the mesh. What you have to do is, and I've given you a component for this. You can bake this color into a material and assign each one of the surfaces in your model, because you're going to bake this as a surface, right? You can assign each one its own material, so you'll have like 700 materials, and each one will be attributed to that thing. The script handles it for you, but you need to run that tiling script in order to get that to work, in order to get it to render for you. Okay? Anytime you do something with mesh color, you got to actually do that step. Bake the material into the surface. Okay? It's convoluted, but that's how this thing works. Like mesh color doesn't translate to like a rendering. Only surfaces will actually render with a material. I don't know why they do it that way. They ought to just make it a material. But anyway, so that's a lot. Let's keep going. Yamaha. Okay. So just some other examples of things. So this one, you can start to find the patterns in this. You could use. This seems to have kind of a stripe that's eroded. Like if you look at the windows, they kind of have bars. You can use an image as a reference to draw those like stripes on your building and then erode it in the way that I described. Right? That could be a pattern for this facade. Another thing you can do, and I won't, I don't think I have a demonstration of this exactly, but you can have a volume, let's say the facade, and you've got the cutouts for it, and you can randomly, you have a system, right? These are on a grid. You have these big windows, medium-sized windows, and small windows, and you could randomly distribute them, okay? Now you can say like, well, Nick, well, it's like totally random. What happens when one, when one overlaps another? There are things you can do in Grasshopper that'll tell you whether some object is inside of another object, right? We did this in the earlier lab. Can't remember. I think it was week 8 when we did logic. We tested whether something was inside a shape or outside a shape, right? You can do that, and then you just eliminate all the ones that are like offending you, right? You run another batch, test them against the previous batch, run another batch. Again, the design of this is in the proportions of the grid, the modules that you've selected, right? And then the randomness is just something that you experiment with as a way of like developing this. Like, I don't think, again, this was painstakingly gone and saying, well, there's an office here, and you need the window here, and you need the window there, and sha-na-na-na. Because when you look inside the building, it's clearly not like ordered that way. In fact, they went way overboard with this. Look at this. The ceiling has these things in it. The windows inside of it does. The columns start like dissolving. If this was a student project, I would say some unkind things. You look at there's even a little checker. They just went way overboard. But this is all the principles that I'm talking about here have been applied to this. It's like a supervillain's lair or something. It's just the motif is like everywhere. The bathroom probably has this. I mean, it's a little crazy. You gotta respect, they went all the way with it. So look at that, like in the space. Now, they did, I mean, it's not like there's like a half window. They did actually obey the grid so that it never goes below the floor. There isn't one that like goes from the office above to the office below. They did respect the floor heights in this. Okay, it's just math. You could actually figure this out. Crazy. All right, here we go. This is my jitter example. So I'll say this. I use jitter in a particular way. There is a jitter component that's in Grasshopper. It is not what I'm talking about. Okay. Jitter in Grasshopper is a kind of randomness that like you give it a list of values and it just kind of shuffles those values around like in an odd way. Okay. Like if you got a bag with 10 marbles and each one had a different number on it, it's just going to reorder those 10 in some fashion. So instead of a random number generator, you know what the numbers are, but the order of them is random. That's Grasshopper jitter. Okay. Sensky jitter is I got a number and I add a little bit of English to it. You guys know pool, like where you put a little bit of wobble on the ball. I take a number and I add or subtract a minute amount to give it a little bit of wobble. That's what this is, right? It's a grid with a little bit of English applied to it. Just in the z-axis. Okay? Does that make sense? I'll show you. All right. Now quickly, I'm running out of time here, but I'll show you my jitter. I need to, once again, I need to draw a surface here. Oh. And I think, oh man, I should have, I should have done this with the surface that I had at home. Because it's doing weird stuff. Okay, let's kill this. Yeah, this one was pretty dependent. I think it was because it was really close to this axis here. Better. I'll call that okay. Okay, I'll get you the actual file that I used with this, but this is kind of disturbingly out of kilter. But let's take a look at this. So, just to proof of concept, right? That's a grid, okay? The jitter comes in here. So I have, basically, it's real simple. I have this grid, and I have all the points on that like grid. I extract the points from the surface using a BREP explode. Take all those points, and I have this random number, which is my jitter, right? Which is my English generator. It has a little bit of negative, a little bit of positive. I take all those points. And I gotta get all the way. Yeah, I know it gets that. That's another thing. Hang on a second here. Yeah, I take all those points and I use that to move them slightly. Okay, makes sense. I move the points. And then so what I did was let's turn all this off. Take a look at this. Hang on a second. Something's turned on here. Yeah, I'll just turn this off. Okay, so I got points. And I got English, so I'll reduce these a little bit. And already it's giving me the difference. Okay, so I just shifted those points. Real easy move, right? Okay, the hard part comes in where I gotta put those back together. And it's not as easy as just like saying, okay, I got a surface. Well, on one hand it is. I can take those points and I can rebuild them as a new surface, because it'll try to do that. Right? Like it's actually tried to like rebuild that. And then if I subdivide that again, it gives that like back to me. Okay, so you understand? So I took the locations of the points, broke them, moved them apart, and then I put them back together again as a surface. Okay. Now the other like huge part of this script is something you don't really have to worry about, but I wanted to be honest with you guys about how this works. This edge is straight. Okay, I shouldn't have messed with those. Okay. Now, I could go into the data structure and exclude these and then only like jitter these, like I could do that, okay? But it wouldn't be the hard way. So the way that I did it was, I took all the coordinates of those points and I just made them all the same, right? Because they would all be in the same z. So I just took the thing apart, made them all the same, and zipped it back together again. And that's what this script is attempting to do. Although, again, because the geometry that I was using when I created this is not present. That's actually, oh, hey, how about that? That did work. But that's what that is. Like, I'm not going to go through all of like the minutia, but what I did was, you know, you can deconstruct the square and get the 0, 1, 2, 3 points, right? So 1 and 2 need to get back in line. So I took their z coordinates and their x coordinates and I reprogrammed them to all be the same. So everyone in that row has the same z coordinate instead of the jittered one. And then I zipped it back together again, offset it and lofted it. Scaled it and lofted it, and that gives me the form. So I just recreated the precedent. I did my own precedent project for you guys. Okay. So pretty cool though, right? I mean, so like jitter is actually a really interesting way to think about things. The other thing I'm going to show you guys as another example, there we are, of jitter. Kill this here. Is this. So I have this another, it's not just for that. You do this. How many times have we done, in CAD, like we want to make a texture for something, or we want to show like a forest or whatever, we go in CAD and try to draw random lines or whatever. We just want this interesting kind of like interference kind of pattern that we create. It's a bunch of lines that I drew. I start with some points. I make some random numbers. I have a random number that's the location of where these things are that I've kind of bumped a little bit. And then I have a random number that they all start off at the same height, but then I go in and I kind of chop off a little bit on the top of each one, and it gives me this idea. It's very regular at first, but the randomness introduces, this is what I mean by jitter, because there's some regularity that I've messed with. It's not totally random. Okay. Again, Sensky jitter, not jitter in a Grasshopper, but that's what I call it, because that's...
What is jitter in Grasshopper?
It's the thing I said, you have a list of numbers that is known to you. You give it a list of numbers, and it resorts it into some random order. The numbers aren't random, the order is random, which might be useful also. Okay, that doesn't sound very jittery to me. I don't know. Jitter to me is disturbing something. I'll have a talk with David Rutan. Right. He'll watch this video and he'll send me an angry letter. Okay, so anyway, again, I don't think that they sat down and like painstakingly like figured this out. I think there's probably just some logic to it. This monstrosity is from the Olympics in London. It's this Coca-Cola thing. You could take a bunch of like planes, right, and give them a random like rotation, random like position, right? They just made this nest of these things, and then they just carved out the space inside of it. I'm grossly oversimplifying it, but again, you could write a script to do this pretty like easily, and it's meant to be like discordant, and then the inside of it is actually like a ramp. It's like kind of a regular space. I know, right? There's some bad. A lot of this is bad. I'm gonna tell you, and these people are gonna email me, and they're gonna be angry with me too. This is a building, and I believe it's in France, and I also don't like it very much. This is like where this gets really bad. It's a concept just overblown. But there are these like panels, and there's some kind of random pattern where they put circles in it. Right? I know, we're all making faces. Somebody like really went through a lot of trouble to digitally fabricate like all these things. Like they were really interested in this like Swiss cheese, building. Maybe that's what it is. It's the cheese depository or something. I don't think so. This is what you should not do. Right? But it's a demonstration of randomness in architecture, right? And it's the fact that like you can fabricate this stuff now. It's not just a matter of like construction. This is all just a matter of like the ability to fabricate these things. So to get to the end of the point, I mean, I think it's a question we have to come to terms with is how should we think about randomness in design? Like there are like ways in which randomness, architects have used it, and there are ways that they've abused it, right? And we have to like find out what we think about that as architects. I think order, in the modernist tradition got kind of boring, and so we wanted to like mix things up a bit, and so we ended up trying to think about ways of adding complexity to designs, and one of those devices is randomness. Even actually during modernism, there were experiments with randomness where you get like, burrows and sort of like the cut-up method, of making poetry by just finding words in magazines and cutting them up and putting them back together again. We'll start talking about that. So even then there were reactionaries. So this is like random. This is noise though, right? This is just like white noise. It's a field of stuff. Now, we may have like a debate about this, but I think it's uninteresting, right? Because it's got no order to it. Like it's completely, random. It's not architecture. Architecture is form, space, and order. I think there's even some order in randomness. There's no order like to this. I don't think we want to build this. I don't think we want to live in this. It's not design, so it's not design, I think. So it's uninteresting. When you get into Jackson Pollock, and you would argue like, well, there's actually quite a bit of randomness in what Jackson Pollock did. Like every time he loaded his paintbrush and he like threw it. Now he kind of knew where it was going, but he didn't know. He didn't know what the viscosity was, what the airflow was going to be, whatever, right? If there was like a tremor in his hand. At some point, he lost control of it, and then it deposited something on the canvas. But he was in control of the colors that he chose, of where he kind of wanted it to go. Like he'd step over here, or step over there, or throw it really hard, or like lob it underhand. I don't know what his technique exactly was, right? And he decided when he was done for the day. Okay, but there's randomness in this. That's actually what's kind of interesting to us, and that's kind of what he was responding to. So this is the kind of thing that we might be interested in too. And computers can like give that to us, right? So order, it can be boring, like complete, strict, order. And chaos can be boring too. What we're looking for is something in between, like complexity, right? So we look at like these gas clouds in the universe, and I think they're kind of beautiful, but there's no, you might say they're random, but there is kind of order to them. Like somewhere in like, people smarter than I am, like particle physicists, astrophysicists, or whatever, understand that there are things that make these things accumulate in the ways that they do, because of the ways that they form, because of other things that are happening in the galaxy, and that's what's creating complexity. Like gas is complex. It's not the white noise. Like I really don't think it is. Like right there's a mixture. There's like this area has less of it. This area has more of it. Something in our brain is like triggered by this that we find appealing. And in fact, if we think about it hard, we can simulate that. So we can do things like where we can actually simulate gas clouds to a certain degree. This is what's called this is Perlin noise. This is a simulation of these particles, and depending upon the attributes, they kind of stick together. This is a model of that, basically. There are different kinds of like noise that we can actually simulate. There are different kinds of algorithms that we can use that can get us the kinds of noise that we want. And I don't have time to go into them, but just so here we have some people that have done work with randomness in art. John Cage, if you're familiar with him, he's a famous composer. He'd done some things with poetry and with musical composition. He has a book called Chance Operations. It's literally things like using the I Ching, which is a very it's like a large set of things that could be random, like in the hundreds. The tarot, cards are a way, like you're drawing cards from a deck, but there's a big deck of cards. Playing cards could be a source of randomness. Dice. And he was interested, and so was Gene Arp, in this composition was completely done by like dice, basically, just like having a piece of paper, throw one die for the X coordinate and one die for the Y coordinate. That's where it's going to go. Roll it again, just make this thing. And the idea is that playing with this idea of the operation of what the artist does, of where the artist is in control of and what they're not in control of, like where the art is. Tim Knowles is a more recent, artist. He does these like studies, these motion studies, where he has a car with a spring-loaded marker in the back of it, and he drives it on the Autobahn, and he just or does donuts with it, or whatever. And it basically, the physics of it and the spring is actually what's creating the drawing. So that his drive is creating the drawing. Okay? He has these beautiful things where he just ties a marker or like a sumi brush to the ends of a tree and lets it blow in the sea breeze. Okay? Very poetic. This weeping willow with like markers on it. Okay? Serialism is the one kind of on the left here. There's this idea that randomness can be complex when it has rules and constraints. So when we start to like say what it can do and what it can't do, and what we like and what we don't like, then we can get some really interesting, really kind of like poetic kinds of things. So there's ideas that you can create a system, and this is what serialism is. It's like you have only certain notes can be played, and they can only be played in a certain order. If you start from one point, you have to end up at another point. So there's serialistic compositions. So there's a system that you play with. Or there's this idea that you create a system that has play in it. So you have this thing, but there are parts of it that you're not in control over at all. Okay? And that's where these things come into. So you have springs or squishy, fuzzy things in it, right, that are giving you this play in your system. So again, you can have rules to choose and play. So you can construct your design rules as a game that you play, and you can play that through the script. You can have an automatic machine that you just put a coin in the slot, right, turn the crank, and see what comes out of it. Okay. This is a project like this is a drawing machine. This is a gerbil in a cage. I think it's the bird actually. Yeah. And this wheel has a motor on it. It's constantly going around, and the balance of the cage, like where the bird is like landing, is actually creating a wobble in it. And this thing is just constantly drawing, basically. So when the bird is like stationary, it's going to keep drawing a line. When the bird gets up, the line like moves. It's almost like a graph of where the bird is in the cage as a circle, and it's just over the entire course of a day, it's going to create a drawing. The bird is random, I think. We can get like very philosophical about that, right? Whether it's predestined or something, right? But this is interesting, right? But somebody decided like the way to represent it, like how to create the mechanism, what color the marker was, how to tune the balance of it to produce this like piece. And there's no way to know like what's going to come out of it. But it is of a. Now I could get different birds, right? And the system would work, differently, right? Change the food. There are other variables like in the system. So what we're talking about here is the theme of the course, really, is designing processes, okay? And we get into different territories. So we can have things like the parameter measures. We're almost like a spirograph, where we have like a set kind of thing. That's a parameter. It has a given radius. You turn it a certain number of times. It's very fixed, okay? If I give anybody a spirograph, they can make these beautiful little spirograph like things, right? That's kind of what's interesting about it. Or you have procedural or generative design, which is a little bit beyond what Grasshopper is really capable of. But what we have are systems that are actually self-sustaining, that are actually like driving. It's like the bird in the cage, okay, right? Where we don't know what's going to happen, and it gets into interesting kind of territory for us. Okay, they're both valid, but we've been spending a lot of time on this side of the playground, and I'm really interested in my work, especially in this side of the playground, right? In the indeterminate kind of processes. And that brings us to Saul the Witt. Do you guys know Saul the Witt? Some of you? Okay, it's early still. This idea, he said the idea becomes a machine that makes the art. Saul the Witt was this serial artist, not with Chex Mix or like Blueberry, but serial as like a series of things, right? SERIAL, serial, like a serial killer, but a serial artist. All right, and he was interested in like making processes for making art that could then be applied to just totally different environments. So he would give you, for like $100,000, the instructions for a painting. And then like draftsmen would have to enact that like painting. And they could enact it like in 10 different museums. He's a very smart guy, actually. There's not just one piece of art that like goes around that can only be hung up in one museum. He can kind of franchise it, right? And it's different depending upon where it's done and who does it and whatever, right? Those are the kind of variables. But he's not making spirographs. I mean, his stuff is still a little bit more flexible. Saul the Witt. He passed away a few years ago. So this is a collection of some of his art. There's one in the Beckler that's actually in the Beckler, like a huge one. So he talks about this idea that to work with a plan is a way of avoiding subjectivity. It obviates the necessity of designing each work. The plan would design the work. So he's saying it's a way of removing yourself from the work in a certain way and really getting to kind of the purity of what you're trying to do. And it's this idea that you're working from a plan. So this is one plan for his piece of art. Like he would actually tell you, you do this color and this configuration, and this is what's going to make the art. But he did not make the art. Someone else enacted that art. He has the plan. So this is one of his instructions. Like you have a 12-inch grid covering the wall. Within each 12-inch square, one arc from the corner. The directions of the arcs and their placement are determined by the draftsman. Right? That'll be $500,000, please. Right? That's what he did. And it's a simple idea. You have a grid, and let's say let's do pick and choose. Right? You have 4 positions for the arc. Make a random number, right? And then this is the composition. Okay, it's beautiful. I think it's beautiful though, right? I think it's really interesting to look at. You see certain kinds of flows in it, right? And you could completely make a million of these things and they'd all be different. But he has the idea. It's just 2 lines of code. Let's call it, right? Okay. Wall drawing. I like this one too. First drafter takes a black marker and draws a line. Next person takes a red marker, one takes a yellow marker, and then a blue marker, and then they repeat the process. That's all it is. And like a game of telephone, right? The line begins to change because the next person traces it differently. And the line, you can see that the line at the top of the wall has a lot of change, but then it begins to flatten out as it goes. Okay? The draftsmen are the variables. They're the birds in the cage, right? Each person that picks up a marker changes the composition. But he had the idea. He chose the colors and the order of the colors. The site is going to affect it in certain ways. Okay. Designing processes. Another one, architectural drawing, called wall drawing, is to basically draw lines between all of the architectural elements and all the other architectural elements. And again, depending upon the space you have, it's going to be a totally different composition. This is measuring chalk. Those chalk strings. But it almost creates this kind of wireframe, model of the space. It activates the space. If I want to throw some swisher there. The serial artist does not attempt to produce an object, but functions as a clerk cataloging the results of a premise. So it's not about the one work, it's about the plan and the possibilities of what that work produces. Okay? See, this is actually a study in the back here of all the different ways that you can create a box with lines. And there's 100 of them. So he's exhausted all the possibility of that. And that's a serial work. So sometimes when we're designing something, we're not designing a building, we're designing all the potential buildings that it could be or all the potential things that it could be. And what we're designing is that program. And there are architects like Greg Lynn, I think you guys have seen some of the stuff with the embryological house and his silverware that he did for Alessi and his he did these pictures where some of them are god awful, but they're all part of the set, so they're all valuable, they're all meaningful, right? Because the process was important to Lynn, not the artifact. Okay? So it's a troublesome thing. So valuing process over product. We've heard about this a lot. We can literally enact that when we get to computation, because instead of slaving over a drafting table, figuring out all these combinations, you can write a program and it'll do it in 30 seconds. Okay? And we get to weird territory. So don't overlook the idea of simplicity. A simple rule, repeated, because repetition is free in the computer. Effort is free. We can make it do it as many times as we want. So think about simplicity. We can always make stuff more complicated, but simplicity, when it's when we apply computation, can become complex. Can become really beautiful. These are some artists I'm going to throw at you before you leave here to take a look at. Marius Watts. He's kind of a graphic artist that does computation-based works. So all these projects have a bit of randomness in them, right? You can ask yourself where does the randomness come in? Well, he's got this series of dots, that are in a circle. But as they go, through towards the center, he's disturbing that you might call it the control points of it are kind of being disturbed as it shrinks. The size of it's changing, and that's what's creating this kind of composition that you see here. He's choosing the colors that he's using. John Maeda is a really famous designer. He is my mentor at MIT. He's president of RISD now. All the stuff that is on computers that you see on the web and Flash and these kinds of compositions, you can blame him for it. He invented a lot of the ideas in the software that we're using to do generative design. This is a simple idea of these things radiating out from a center. there are certain colors that he's choosing, and where they overlap, they create like these sort of like discordances. I mean, so it's a very we can talk about how he actually does this, but this is just a sort of a pseudo-random composition. The same with this one, starting with a circle, and then he just continually creates like a lozenge shape over it, and he just keeps doing it, and then they become darker in the center. So it's just this idea of like agreeing on these things. But choosing the right colors, choosing the right method, is what makes this an interesting composition, right? Another John Maeda, just diagonal lines that are jittered, with 2 colors. I think it's a really interesting piece, and his software can make tens of thousands of these, right? So think about these. Again, taking advantage of the colors of a printer, yellow and cyan and magenta and black, and allowing them to overlap each other. Okay, to actually create this composition. More Marius Watts. This idea of using curves, but actually using vertical lines and changing the spacing of the vertical lines to create this composition. Jared Tarbell is another one. Tarbell is doing stuff with just pixels of color. So these other guys are doing shapes. Tarbell is actually doing accumulations of pixels in certain orders and allowing the pixels to disturb each other. His work has more of a sandy kind of quality to it. So check these guys out. This is just a series of grids of these things, and then a series of vertical lines, in a very tight field. So like rope and sand, randomness. Okay. So taking the full gamut today from architecture to kind of graphic art. But again, the theme is for you guys to begin to think about in your work, like what kinds of processes do you want to explore? There are things that you could do by hand. We always talk about like having a system for designing your building. What if that system were actually computational? What if it were something that you could play with and explore, right? What kinds of things could you come up with? Could you surprise yourself? That's what we're interested in. That's one of the things we're interested in comp methods, okay? And that's what's happening out there, in the world of design right now. Okay, so if you're interested in this stuff, let me know. Think about that grant.